Welcome to the first lesson in chemical equilibrium. In this unit, we're going to look at the basic principles of equilibrium, and our focus will be on systems that are mostly homogeneous gaseous equilibrium. In the units following, we will look at applications of chemical equilibrium, and we will focus on acid-base equilibrium and solubility equilibrium. One of the best examples of a simple system at equilibrium is if we have a container of water. Here we're looking at something like this. If you had a container of water sitting on your desk at home and there was no lid on the top, you know that the water would evaporate. If you close that system, as you know, if you looked at it for hours and hours and hours, the volume of the container, the water in the container, would not change. That does not mean that evaporation has stopped. What it means is that the system is at equilibrium. Because while evaporation is happening, condensation is also happening. So in this container, we have H2O as a liquid being converted into H2O as a gas, and at the same time we have the H2O as a gas being converted into H2O as a liquid. So we have evaporation and condensation happening at the same rate. Because they're happening at the same rate, for every molecule that evaporates, another molecule condenses. When we look at this system, it doesn't appear that anything is happening, despite the fact that it is quite dynamic. So we refer to these systems as dynamic equilibrium. Here are some of the principles of a dynamic equilibrium. It's a reversible reaction, which is a new idea. You're used to, in grade 11, looking at reactions that have only a forward arrow. And we think of chemical changes as being ones that are not reversible. The reality is there are many, many reactions that can be reversed and can establish an equilibrium where the forward and reverse reaction are happening at the same rate. In order for a system to stay at equilibrium, the system needs to be closed. In our example with the water evaporating, if the system was open, only the forward reaction would be happening, or it would be happening at a greater rate, and therefore the system would be changing over time and would not be at equilibrium. In a system that's at equilibrium, the macroscopic properties are going to stay constant. So because the rate of the forward and reverse reaction are happening at the same rate, the amount of the reactants and the amount of the products are going to stay the same for infinity, basically. So what that means is that the macroscopic properties, or if we look at it from the outside, it looks like nothing is happening. So the pressure is going to stay the same in the system. The volume is going to stay the same in the system. The concentrations of the reactants and products are going to stay the same, which is going to lead to a color that is constant of the system. We'll examine this last principle of equilibrium, that it can be achieved from the forward and reverse direction, in a few moments, and through the activity that you do in class. We'll next look at a few examples of chemical equilibrium. So we've talked about scenarios where we've got a state change, so we can have an equilibrium between a liquid and gas. We can also establish an equilibrium between a liquid and a solid of the same substance, like water. I talked briefly about the fact that we're going to look at applications of equilibrium, and one application of an equilibrium is solubility equilibrium. When you have a saturated solution, that's the point where you have the maximum amount of dissolved substance in the given amount of water you have. Although it would appear that nothing is happening, at the molecular level, there's actually a dynamic equilibrium that's happening. There's an equilibrium between the solid that you're dissolving and the aqueous version of that solid. So if you were to zoom in and look at a saturated saltwater solution, you would see salt crystals dissolving and salt crystals crystallizing at the molecular level. Macroscopically, or in a large view, if you looked at it, you wouldn't see anything happening. The other application that we'll be looking at is with acids and bases. And you've learned about the difference between a strong acid and a weak acid, or a strong base and a weak base. The same principles apply. When you have a strong acid, as you know there are 6 of them, they completely dissociate. So there's only one forward arrow. If you have hydrochloric acid in a solution, all of the acid is going to dissociate into hydrogen and chlorine ions. On the other hand, when you have a weak acid, a classic example being vinegar, it doesn't completely dissociate. So while some of the acid molecules are dissociating to produce H+ and the acetate ions are recombining with the H+ to form vinegar molecules. And what happens when you have a weak acid is that you establish an equilibrium. We're going to study these in great detail in our second and third units. An example of a gas that, another equilibrium, a gaseous equilibrium, is one where we've got the brown N2O4 gas in equilibrium with the colorless N2O4 gas in equilibrium with the brown NO2 gas. And what we'll show you is that if you've got 2 different tubes, if you look at the tube for a given amount of time, the color of the gas is not going to change. It's going to be at the same concentration of brown. If I heat up one of the tubes, what you'll see is that the color will change and that it'll actually become a darker brown. If I cool it, it will become lighter. And what this is showing you is that equilibrium is temperature dependent. And although we can achieve an equilibrium at 2 different temperatures, the concentrations of the substances at those given temperatures is going to be different. We're going to examine that in greater detail moving forward in this unit. These little graphs here show you that we can achieve equilibrium from different scenarios. And it also shows you how to identify graphically when we have achieved equilibrium. These graphs are concentration versus time graphs. And as you can see, in each one we start with different amounts of N2O4 and NO2. In the first scenario, we start with all NO2. In the second scenario, we start with all N2O4. And in the third scenario, we start with a certain amount of each in the vessel. All of these systems are able to achieve equilibrium, and we know that they've achieved equilibrium when the concentrations of both of the gases have reached a constant. So it's the point where the graph flattens out. Once the graph flattens out, that does not mean that the reaction has stopped. It means that we've achieved an equilibrium. So at this stage, the system will continue to be dynamic and have both the forward and reverse reaction occurring. They'll be occurring at the same rate. Something that you can note about these graphs, when you've got a concentration versus time graph, the slope of the tangent at any given point is the rate of the reaction at that given point. So we can see that the rate of the reaction actually changes as time goes on. So the forward reaction might start out being fast and slow down towards equilibrium, while the rate of the reverse reaction might speed up, or vice versa. This website is a great website for you to look at. Okay? It's got an applet in it that allows you to investigate a system achieving equilibrium. You can choose different temperatures, and you can choose different starting materials, and you can monitor it graphically and identify when equilibrium has been achieved. And I'd encourage you to take a moment to look at that website and play around with the applet. Now, I've talked about the fact that when we reach an equilibrium, we reach some kind of a constant concentration of both the reactants and the products. And you're going to be able to, in this unit, be able to calculate and determine what those final equilibrium concentrations are. In order to do that, we need to establish an understanding of what is called the equilibrium law. And to do that, we're going to investigate experimental data from this equilibrium. Okay, so we should have equilibrium arrows here. So we're going to study this equilibrium of I2 reacting with H2 to produce HI. I2 is a purple substance, and when we're studying equilibrium, we need a way to measure one of the substances at equilibrium. If something has a color, we're able to use the intensity of that color in order to determine its concentration. As you'll recall from last year when you did Beer's law and the copper sulfate experiment, you used the intensity of the blue in solution in order to identify the concentration of an unknown solution. And this is how this experiment was completed. In this experiment, what they did was they took 4 different scenarios. At the moment, you can see 3 of them, and the 4th one is on the next page. In each scenario, they started with a different initial amount of each of the substances in the flask. Okay, and you'll see that they're different scenarios. So in the first one, we start with H2 and I2, and no HI. In the second one, we start with some I2 and some HI. These conditions on the left-hand side are our initial conditions. Then we look at the other side over here, and what we have is our equilibrium conditions. And the short form for equilibrium is the symbol here, equal with a little tilde, and I'll use that frequently. If we look at the values here, we can see that we started with 0.1 molar H2 and 0.1 molar I2. At equilibrium, we have 0.0222 of I2. And that's what they would have measured in the lab. The other 2 values, the value for H2 and HI at equilibrium, they would have determined stoichiometrically. If you look at this, you can see that the concentration of the I2 has changed by a value of 0.0778. It has gone down by 0.0778. So stoichiometrically, if we look at the chemical reaction at the top, we know that for every mole of I2 that's used, a mole of H2 is used. Okay, so what that means is that the H2 has also decreased by a concentration of 0.0778 in establishing an equilibrium. And so it will have the same equilibrium value of 0.0222. The HI, because it has a 2 as its coefficient in the balanced chemical equation, for every 1 mole of I2 that is used up, 2 moles of HI are produced. So for the HI, it's increasing in concentration. It started with no HI in the system, and it's going to increase by 2 times 0.0778, okay, which is where we got the value 0.156. So you can go through each of the 4 scenarios and follow that path. You can look at what the change is in the I2 based on its initial and final concentrations, and you can see that the amount of H2 and the HI in the system are calculated using stoichiometry. What we have following our 4 examples is a summary chart. We've got experiment 1, 2, 3, and 4, and this chart here shows the equilibrium concentrations of the H2, the I2, and the HI. And so you can take a moment and compare, see where I got these values from. Now, in this Excel spreadsheet that you're looking at, what we did was we took these values and we plugged them into this relationship. We took the concentration of the HI and squared it, and we divided it by the concentration of the H2 times the concentration of the I2. For each of the 4 scenarios that started out to be really different but established an equilibrium, what we can see here is that we get a constant. And the average value here is 49.5. This expression is called the equilibrium expression. And the equilibrium law is that this expression, this scenario that I plugged into, will always equal a constant for a system that's at equilibrium. Now, this expression, the H2 squared minus the HI, okay, we didn't just pull it out of a hat. Okay, it's actually connected to our balanced chemical equation. So if we look at this expression, we can see the relationship. As you can see, the products are in the numerator. The reactants are in the denominator. When we had more than one reactant, we multiplied them. So it's the H2 times the I2. And this 2 that we're using as our exponent is the coefficient from the balanced chemical equation. So for any reaction, we can write an equilibrium expression in this same format. And it defines the ratio of the substances in the system at equilibrium. So whenever this system achieves equilibrium, it's going to have some kind of some ratio that will fit into this expression and equal a constant. So let's look in general. First of all, this expression is called the law of mass action. So for a reversible reaction at equilibrium and at constant temperature, that's an important point, a certain ratio of reactant and product concentrations has a constant value. And the certain ratio is the ratio that's connected to the balanced equation. So if we look at a general balanced equation, this one here, where we've got reactants A and B and products D and C, the law of mass action expression, which is also referred to as the equilibrium expression or the equilibrium law, is as follows. We take each product, the square brackets mean concentration, we take the concentration of C and raise it to the C, the concentration of D and raise it to the D, divided by the concentration of A to the A times B to the B. So it's products over the reactants, and each of the individual reactants and products are raised to the exponent based on the coefficient in the balanced chemical equation. You'll see here that I have the equilibrium constant expression listed as Kc. This means that it's the equilibrium constant expression in terms of concentrations. We can also, and we'll use quite regularly, the equilibrium constant expression in terms of partial pressures. And that we will refer to as Kp. You'll recall that the partial pressure of a substance, so if I want the partial pressure of A, that's equal to the mole fraction of A times the total pressure. And you find the mole fraction which is X, by taking the moles of A over the total moles. Okay, sorry about that. So total moles there. Okay, and this comes from Dalton's law of partial pressures. So the individual pressures add up to the total pressures, and they're related to the relative amount of moles in the system. In order to use Kp, we usually we use it for systems where there is nothing in solution. So things must be gas, solid, or liquid. And we'll do examples in a few moments. Now the other note that you have here is that there are no units for the equilibrium constant. We don't have any units because they're not going to help us and give us any further information. So the equilibrium constant value is a unitless expression. We could establish units. Sometimes there would be none. Sometimes it would be mole cubed over liter cubed. But it's really not going to give us any further information, so it's an unnecessary thing to do. Now in equilibrium we have homogeneous equilibrium and heterogeneous equilibrium. A homogeneous equilibrium is a reaction where all the reacting species are in the same state. They're all gases, they're all aqueous. A heterogeneous equilibrium is one where the reactants and products are in different states. So if you look back at the examples on the first page, the ones where we had the solid going to aqueous, that would be a heterogeneous equilibrium. When we're dealing with weak acids and bases, those are all aqueous, and therefore that would be a homogeneous equilibrium. This is important to note because when you have a heterogeneous equilibrium, the pure solids and liquids will not be included in the equilibrium law. The reason for that is because when you have a heterogeneous equilibrium, the amount of the solids and liquids will not affect the equilibrium. So think of a saturated solution for a moment. You've got an equilibrium between a solid and something that's aqueous. So you've got a heterogeneous equilibrium. A saturated solution, as you know, is one where the maximum amount of substance is dissolved. So if you have this equilibrium and it's already saturated, adding more solid to that system is not going to make more dissolve. So the solid itself is not going to affect the position of the equilibrium, the amount of reactants and products that we have. The same would be true for a weak acid. Adding more pure water to the system isn't going to change the percentage of the acid or base molecules that are going to dissolve. So when you're writing expressions, you're going to leave the solids and liquids out of the expression. So we've got an example here of a homogeneous equilibrium between nitrogen and hydrogen to produce NH3. And we're going to write the expressions for these reactions below. So we've got the Kc, products over reactants, so the concentration of NH3 squared over the concentration of N2 times the concentration of H2 cubed. The Kp expression for this is the partial pressure of NH3 squared divided by the partial pressure of N2 times the partial pressure of H2 cubed. So as you can see, the Kc and the Kp expression are written in the same format. The change is the concentration to the pressure. So let's look at these examples here. We want to write the Kc expression and the Kp expression. Okay? The Kc for this reaction is the concentration of Br2 times the concentration of Cl2 divided by the concentration of BrCl squared. Similarly, the Kp expression is going to be the partial pressure of Br2 times the partial pressure of Cl2 divided by the partial pressure of BrCl squared. In this second example, we've got a heterogeneous equilibrium. So we've got two solids. They will not be included in the equilibrium expression. We don't think of them as having a value of 0. We think of them as having a value of 1 in the equilibrium law. So for this one, it's going to be the concentration of O2 to the 5. 1 over the concentration of O2 to the 5 because it's a reactant. And the Kp for this expression will be 1 over the partial pressure of O2 to the 5, which in this case would be the total pressure because there's only the one gas. And you can try the next example, okay, on your own. Okay, and for that one, there will only be a Kc. Now, there's a relationship that exists between Kp and Kc, and we need to be able to convert between the two. And they're connected through the ideal gas law. So, as you know, the ideal gas law is Pb is equal to nRT. And as you know, concentration is equal to nRV, N over V. So if we take PV equals nRT, we can rearrange that, move the V over, and what we actually have is that the pressure of a gas is equal to the concentration of the gas times RT. So what we've got here is we're going to look at just a general equilibrium between A and B. And if so the K P for that is going to be the partial pressure of B to the B over the pressure of A to the A. And so if we take PV equals nRT, okay, we can substitute the pressure for N over V RT to the B, divided by N over ART to the A over V. And in the next step here, what I've done is I've taken out the RT. Okay, so I've taken out the RT, and because this is a division, as you know, with exponent laws, this is going to be B minus A. So what I've done is I've taken out RT, so it's RT to the B minus A. And what I'm left with is the moles over volume to the B and the moles over volume to the A. And hopefully what you can see here is that this is actually the concentration of B to the B over the concentration of A to the A. Which is the Kc value. So Kp is actually equal to whatever the Kc is for a particular equilibrium times RT to the B minus A. So that's in general for this little equilibrium with just two substances. In general, if we've got more than one reactant and product, you could look at the same derivation, and what RT needs to be raised to is to the change in N. And the change in N is the difference in the sums of the coefficients for the reactants and the products. So delta N is going to be equal to C plus D minus A plus B. And this is the important expression. So Kp, the equilibrium constant in terms of partial pressure, is equal to Kc, the equilibrium constant in terms of concentrations, times RT to the delta N. The R that we're going to use here is going to be our atmosphere's R, and what you're going to find is that when you're dealing with equilibrium, you're going to be using atmospheres to study your gases. The temperature here needs to be in kelvins, because as you know from the gases unit, anytime you're studying gases, the temperature needs to be in Kelvin. So recall that a Kelvin is degrees Celsius plus 273. So what I'd like you to do at this stage is to look at these examples and work through them on your own, and we will check our work, and we'll see how you do. At the end of this, you'll be able to complete the practice exercises in the textbook, and you'll be able to do online Equilibrium 1. And I'd also really encourage you to read section 14.1 and 14.2.